sit there forever, but had to have a beginning. Came out of the mathematics first, out of this one insight into the way that things fall back in 1915. In fact, it's a Belgian priest who first did it, called Georges Lemaitre, who said, he wrote to Einstein and said, "Your theory predicts there was a day without a yesterday." It's a with poetic idea. A day without a yesterday, a moment when the universe began. And Einstein wrote back to him and said, your mathematics is good, but your physics is lousy. Because Einstein didn't want to think that his theory predicted an origin of the universe. But subsequently, as we made observations of the universe, we found that if you look at distant galaxies, they're all rushing away from each other. That was found after this theory, which confirmed the idea that the universe is expanding, which confirmed the idea that once upon a time it was in a very small space, and that's the theory of the Big Bang. But it comes from some mathematics and some ideas about gravity, which I think is a wonderful thing. Now, I've only got about 10 minutes left or something. I wanted to give you another example of how we can approach these ideas. So that's theoretical physics and mathematics being extremely powerful and making predictions we can test, which lead to the idea of the origin of a universe. The other way to do it is to say, well, so the universe was very small 13 billion years ago, it was very hot and very dense. Can we recreate those conditions in the lab, in the laboratory, to see how the physics works? And the answer is you can, and we do. And this is where I do my physics when I'm not messing around standing on volcanoes making television programs, which is the Large Hadron Collider at CERN in Geneva. Its job is to recreate the conditions that are as close to the conditions of the origin of the universe as possible, so we can do experiments and test to see what the laws of nature are in those extreme conditions. So here it is, it's 27 kilometers in circumference. Its job is to take protons, which are the nuclei of hydrogen atoms, and accelerate them to 99.999999% the speed of light, at which speed they circumnavigate that ring 11,000 times a second. So you imagine particles going around there 11,000 times a second. The top bit is Switzerland, the bottom bit is France, so it's in 2 countries, a tremendous engineering achievement. The whole thing, by the way, runs at a temperature of 1.9 degrees above absolute zero, so at minus 271 degrees Celsius or something, which is colder than the space between the stars. So this is one of the coldest places in the universe, all of it, in order to accelerate those particles around. We cross those particles, one beam going one way, one beam going the other way, in 4 places on the ring. The beams themselves are no bigger than the diameter of one of your hairs from your head, but they carry the energy of an aircraft carrier travelling at 30 miles an hour. We cross them in 4 places, and in those places we recreate the conditions that were present less than a billionth of a second after the Big Bang, 600 million times a second. And we take pictures of them, and that's our physics experiment. We take the pictures in objects like this. This is like a digital camera. You see that, you probably don't see, but if you can just see these little blobs there, those are people on the scale of this digital camera. So it's enormous, 44 meters wide, 22 meters in diameter, 7,000 tons of digital camera. The collisions happen in the middle there, and the job of this is to take the pictures. So really, it's like a time machine that you can take back to the origin of the universe and watch what happened. I'll just show you a couple of photographs of this thing being built. I should tell you, by the way, if I go back, you see these things on the diagram. These are magnets which can bend electrically charged particles, so we can work out how fast they're going. And this is a real photograph of one of those magnets going down. This was about 10 years ago now when we built the machine. This is the Large Hadron Collider itself, which accelerates the protons. And this is what it was trying to do. So you say, what was it trying to do? It was trying to test another bit of maths. This is a bit of maths which is a bit more complicated than Einstein's bit of maths. But it's a remarkable thing. It's called the Standard Model of Particle Physics. And it's got everything we know in it about every fundamental force of nature, about nuclear physics, about electromagnetism, about radioactivity, the whole lot. Everything other than gravity is in there, in the top 2 lines, and the bottom 2 lines were added again for mathematical reason. Just like Einstein had that vision, that thought of someone falling off a roof, tried to explain the strangeness of gravity, came up with an equation that predicted the origin of the universe. In this case, these two lines were added in the 1960s, so a long time ago, 50 years ago, by physicists like Peter Higgs and others, in order to fix the mathematics of electromagnetism and all those things. What do they predict? Well, they predicted, again, for mathematical reasons, that the universe is not empty. If you take all the stars away, or go to an empty place in space between all the stars and galaxies, it isn't empty. Empty space isn't empty. So that means that if you took all the air out of this room and looked at a little place somewhere up there near the roof, it still wouldn't be empty. If you sucked everything away, it's rammed full of something, which happens to be this thing there. That thing is called the Higgs field. So it's literally like the universe is full of treacle. Empty space would rather be full of things, Higgs particles, than not full of things. What a strange idea that is. But actually, it turns out that that mathematically predicted idea is correct. And think about it, what the theory predicts is that in every cubic metre of space now, so you're stood in about a cubic metre of space, in that cubic metre, there's you, and there's some air surrounding you and all those things. There's also the Higgs field, and there's more energy in the Higgs field in that cubic metre that you're standing in now than the sun outputs in 1,000 years. 1,000 years of solar energy per cubic metre. That's what the theory predicts. It sounds weird, it sounds almost as weird as Einstein's theory, but what we did is we built these detectors, there's another view of it, and we took some photographs, and this is one of the photographs that we took a few years ago now, which is a proton-proton collision with lots of things flying out, including these 4 red lines here, which we think are the remains of a Higgs particle being made and falling to bits. So we have a theory, mathematical theory, that predicts something very strange, but turns out to be true. So that really does mean we're swimming through a Higgs field. Now, I should tell you what that does in the theory, by the way. This thing is, if you look at your hand now, it's solid, it's made of stuff, made of matter. And you might say, well, why? What does solid mean? What's mass? What is it? Well, in this theory, which turns out to be right, because we found the evidence for it, mass is the interaction of the particles in your body, the most fundamental level, with the Higgs field that fills all of space. So the real picture is that you exist, you're solid, you're built out of atoms that have mass at the most basic level, because those little, let's say the electrons in your hand now, they're bouncing off Higgs particles, talking to them, interacting with them, just like pulling something through treacle slows it down. That interaction slows them down, gives them mass, and that's why they're solid, and that's why they can form atoms in the first place, and that's why you exist. And the idea is that that happened. Empty space became filled with Higgs particles less than 1 billionth of a second after the universe began, as it expanded and cooled. A remarkable thing. So I've just about run out of time. I've got to take a couple of questions, but what I would like you to go away with, there's one thing that I'd like you to take away, it's this, that science, it can be about many things. I've talked about fundamental physics here, and I've talked about 2 examples that I find very interesting, which are areas in which you think about something, you do a bit of maths, you make a prediction, and it predicts something remarkable that we then discover to be true. In this case, the origin of the universe, the existence of a Big Bang itself, which is now verified by 1,000 experimental observations, or something fundamental about why we're here. There's this weird cosmic treacle that permeates all of space, without which you wouldn't have structures like atoms. That's fundamental physics. There are also fundamental questions in biology. We're beginning to approach ideas about the origin of life on Earth 4 billion years ago. What could it have been that started life on Earth? How does a dead planet become a living planet? We're beginning to be able to ask questions about the structure of materials. How can you build stronger materials that build lighter aircraft? You'll see in the STEM area over there, you've got industrial applications of advanced thinking, technologies and science. I think there's always something in it for everyone, whatever you're interested in. But the power, I think the power of this approach of looking at the world, of saying, well, we're going to follow our ideas through, make predictions and check them against reality, is quite remarkable. And I hope that many of you who are interested in sciences, of whatever persuasion, some of you at least decide to go on to start answering more fundamental questions about the universe. So thank you very much. We might have time for a couple of questions, but thank you.